Yeah, okay, let's start. So, welcome everyone to the week 5 lecture 1 of live session. So, before starting, just a small announcement. I have uploaded the previous week's Google Colab notebook in the Meets event. So, like meeting notes event. So, if you go over there in the previous week, you will find the notebook over there. Okay. And the second thing is that in the previous session someone was asking like the difference between using this pipeline as compared to the column transformers, right? So mostly what I got to know is that column transformers is mostly on like a pre-processing technique, which uh, normally what it does is that it applies some kind of tools or technique over the columns, selected columns, and now those columns can be one or more than one, even the whole data sets. But whereas in the pipeline section, what happens is that we apply the technique. The techniques as you can consider those as steps before we fit a model. Uh, Google, will you please give link of Google Colab link here? Okay, let me just okay, I will get over it. Okay. So yeah, what I was saying is that in the pipeline section, what happens is that we have the whole data set. We are applying and some steps over there, some steps which are essential for fitting the model, and we are bunching them together in the form in a one line. You can say that, and that's of course since we are performing some kind of steps, so it inherently means that we are doing it sequentially. And since in the column transformers, what we are doing is that we are applying some tools or techniques in each of the columns. So it means that the columns are independent. So if we change one of the column property, it is independent of the other column property, right? So it can happen in parallel. So that's also, so these are the distinctive features of these techniques, the pipeline and the column transformers. Now coming back to the Google Colab, yeah. So if someone can share their screen and go to the Google Events calendar, I need one volunteer for this. Anyone?
Sir, I'm sharing.
Okay, I am sharing, sir.
Uh, okay, Gyan Prakash can share. Yeah,
Okay, sir.
yeah, please unmute. Okay, let me mute it. Okay, go to the Google Calendar. Yeah, go to the previous week live session, Thursday's live session. Mm, yeah, and now go to the yes. You got yes, that one. That one. Yes. Okay, the permission is not there. Let me give you the permission. Uh, just a second. Mm. Okay, can you refresh it?
Yes, sir. Sir, it's giving same.
No, no, request sent won't.
Okay, I am reopening it.
Okay. I changed the Google Access link just now. Uh, anyone with the link editor? Okay, let me see if I can now if it happens or not. Yeah, can you just check it now? Use Control Shift R.
Okay, sir. Control Shift R.
Okay. Okay, maybe I can just paste. I think it's not working then.
Okay.
So it is
Okay.
asking for the request surface.
Yeah, yeah. I think there is since this Colab notebook has been done on a different Google account, so maybe there is some issue. Can you click this link?
Yes, sir.
Can someone else also try and see?
Sir, it is showing some error.
So it is having
Whenever
this
I
error.
clicked on the link given in the message box,
Yeah, sign in error, something like that.
Now, it's opening for Ashit Kumar Nayak. Okay. Yeah.
Yes, yes. It's
Okay.
opening.
Yes. Okay. Fine. So what I will do is that from the next day onwards,
now it is
yes, yes. So from the next day onwards, I will just paste the this Google Colab link at the end of this event section, right? So yeah, so this week 5 Google Colab will be shared on Thursday. Okay, so let's start. So yeah, today's agenda will be the week 5, the first part. We will go through this polynomial regression. We'll understand what is polynomial regression and how to implement it, and then we will use the pipeline part so that you can appreciate like how pipeline could be used for kind of problems. Then we will go through the penalty part, the L1, L2 penalties. Yeah, I think you can stop sharing the screen. Yeah,
Okay, sir.
yes. We will go to the penalty part, and in the next session, we will go through the hyperparameter tuning part, right? Okay. Let me share my screen. Okay. So for my own ease, I have written some of the codes over here just to so that I don't have to search all those things again and again. But again, we will go also through the documentation to tweak some of these codes and to see what are the changes reflected on the data set. So now today we will go to the polynomial, right? Polynomial regression. Uh, yeah. Please. Yeah.
sir. Previous link is regarding week 3 or week 4. Already you have sent one
If
link.
that was its week 4.
Okay,
Yeah. Polynomial regression scale. Yeah. Please mute yourself. Okay. Yeah. Okay. Fine. Mm, okay. So let me use the. Okay. First, let me import some of this data set. So diabetes data set we have looked into. Uh, Let me use this California housing data set maybe. So what was the net fetch California data set? I think that was the name. What was the name? Yeah, fetch California housing. Okay, let me bring it over here. Mm, pandas speedy. Okay, and what we are going to do is that we are going to uh, housing is this one. So we did something, fetch California, this one as frame equals to true. Okay, we'll do this. We'll take this data set and okay, why is it not saving? Okay. Okay, now we have fetched the this thing. Now we will just, as usual, we will again separate the data into training set and testing set. Okay, I have not imported the train test split part, so that's why it is showing some yellow color error. Yeah, what was the name of that? Yeah, train test split. Okay, yeah. So it's splitted. Now we will go to the polynomial, this thing, polynomial regression. So first we will import this polynomial features. We will also import the standard scalar. So if we, in the future, if we want to implement that, we will, for that purpose, we will import it. Yeah, okay, it's done. Uh, Now we will implement the polynomial features. So what happens is that in the linear part, what we saw is we were trying to fit a linear line on the data set. So we had some kind of x comma y. X were the dependent variables, y was the independent variables. We were having this. We were saying that some mixture of this x was had some contribution to the y. So this contribution of x was fitted in as a linear line. As in the linear sense, it was a straight line. We were trying to fit a straight line, and from that straight line, we were trying to see what could be the predicted result. In other sense, you can say x and y are correlated in a linear fashion. But when we are talking about this polynomial polynomial feature, polynomial regression, what we are going into it, that we are saying that no, it's not like there is a linear uh, relation between them. There is some kind of curve, or the relationship is linear in the sense they are linear in some kind of upper dimension. And for that upper dimension, what we are trying to do is that we are trying to fit a polynomial curve over there. And that polynomial, after fitting that polynomial, yes, anyone wants to
So
say
is
something?
it like kernel regression?
In some sense, yes, because first we were trying to fit, moving this x training part training things into some kind of higher dimension, some kind of degree things. And after that, we are fitting this, when you will go through it, we are fitting the same linear regression or the SGD regression. So in one sense, you can say yes. But again, if you plot it again, you will see some kind of curve over there, right? So yeah, that's the thing. In other words, you can also say that you are trying to fit a normal curve, and to fit a normal curve, you are doing some kind of transformation to the x to bring it some introducing some kind of degree into it, and then you are relating that those degree kind of data or the features, x features, to the y in a linear fashion. So previously it was some y equals to mx plus c. Now it is some mx square or mxn plus c, like that, right? Okay. So this is the thing. We have some degree. We have this polynomial features which will be applied over to this data. Polynomial fit transform. This is transforming the data into that degrees, to that degree, and this extends just moving that those data to the degrees in the higher dimension, right? So yeah, first we will look into degree 2, then maybe we will see what are the advantages of higher degree and lower degree. right? Okay, now we have fitted a degree 2 polynomial. Okay, now this is done. Okay, and now of course we will fit a normal regression model. uh, yes,
Sir, this polynomial features is the transformer,
polynomial features is the,
whether it is a transformer or regressor, sir. Poly is equal to polynomial features.
it is a transformer.
It is the transformer, okay?
Yes, now we will fit. This is the features you can see. Okay, this is the next line. Here I have fitted this X train poly comma Y train. So this is the model. Okay, I have not okay, I have not imported this thing, so let me just import. And yeah, all this thing, let me, okay, maybe I can just keep it over here. Okay, fine. Let's see. So this is the model equals to linear regression model dot fit X train poly Y train. So let's train this model. Okay, now this model has been trained, and now what we are going to do is that we were going same thing, we are going to predict that model, and we will try to visualize this, right? So let me just for
Sir,
the ease. Yes.
sir, can we see the first five records of after transformation?
Mm-hmm. You want to see that?
Yeah, yeah, yeah.
Yes, sure.
Just to know from your side how it will be transformed after transformation.
Yes, sure. Okay, so let me just color this thing, okay, right? For better visualization, let me, okay, I have not imported this.
So what I am asking exactly is before transforming first five rows, five records, how they will be.
Yes, I got it. So that's why I am trying to print visualize both the things before transforming and after transforming, right?
Okay, okay, okay. Not only in the graphical mode, generally in the data frame format also.
Okay. Let me just first let me show you if how it looks like in the color equals to red. This X level and Y level are not necessary now. Maybe I can just name it some X values, and this is some Y. Degrees by title is not needed now. Let's see what happens. X and Y must be of same. So what happened? Okay. So X train is a, okay, let me just print it. So we were using all the columns, right? So that's why it's throwing some error. So, yep. Strain poly, and yeah, this is the X train poly, right? Let me just print it out. You can see, right? Some 1.4 point something is there. And similarly, if I just take a note of this, if I train this, this is the thing. Got it? Is it fine? Please, yes or no?
Okay, okay. After transformation, this is the scene.
Yes, yes. No, this is before
Okay,
transformation.
okay, okay, okay.
Yeah, but for if you want, yes. Anyone, please. Yes.
Sir, I joined a bit late, sir. Can you explain what is polynomial features function?
Polynomial features, what we are trying to do is that instead of fitting a normal line onto the data set, we were saying that there is a linear relationship between the X values and the Y, that is the dependent variable and the independent variable. We are saying that there is some kind of higher order relationship. In one sense, you can say it's a polynomial relationship where degree is greater than 1. So what we are,
So that means we are going to fit curve instead of a line.
yeah, instead of a curve, that also we will visualize. We are trying to fit a curve. Exactly.
Sir,
So
how we are figuring out that a curve will fit the data set?
that also we will see. So that there are different techniques now. That these things, whatever questions is coming on your mind, it will be cleared out when you see those things visually. So there are various techniques for that. We will go through it one by one. Okay. Now first let me, okay. So since there are various features, right? So maybe we can just take one of the features, because this will uh, print some kind of okay, just a thing, just 1 minute. So this will throw some error over here, because we will here we are using all the data set which is not required. So yeah, first let me just mean square error is 0.45, right? Now let's do something else. Maybe what we can do here is that we can, instead of using all the features, what we can do is that we can use some of the features, not all some, I don't know, 8 features are there, right? So maybe we can use okay, this is the thing. Maybe we can use some, I don't know whether this will work or not.
Sir, can we use feature selection here?
Feature selection as in?
So now you are going to select some of the features out of 8.
Yes, yes, that only I was I'm trying to do now.
But can we use any feature selection methods for this?
That feature selection means that which features will be more like provide me a more confident result of what could be the y value. In that sense, you are saying?
Yeah. There are some methods that was explained in this course.
Can you just name one of the methods? Then we can go through it.
One thing, sir.
Select k best.
Select k best and select k best features, and it may use some one thing features.
Now here I have taken latitude. Okay. Yes, please, please.
So feature SKLM library. From SK11.feature extraction, we can select that is what I am saying. So select k best out of given features.
K best features. No, I'm asking what is the technique being taught over there.
Okay, I am saying, sir. I am referring the study material given.
Yeah, sure.
Okay, there are filter based method and wrapper based method, out of which, for example, RFT. Select percentile. In the brackets, chi-square equal to 2, percentile equal to 20, like that. And for select k-best out of in the bracket, we can give chi-square as the scoring function.
Okay. Yeah, can you just type it over there in the chat, like in the chat window? So maybe we can, after seeing the visualization, we can go through it again.
Yes, sir, I will do, sir.
Yeah, sure. Okay, yeah, here I have taken latitude, so I don't, okay. Maybe I will just go through the first, this thing, what they call this, visualization part, and then we can move forward with, I think, Sanjeeva Rao, whatever he's saying, we can move forward with that. Okay. Anyway, so yeah, we can take one of the features. I don't remember the exact name of the features. So let's take some this house average as I think latitude won't affect much on this data set. So let me just use the house edge. Okay. Yeah. Okay. This thing has been done. Okay. Degree equals to 2. What happened? Xtrain poly equals to xtrain and dot fit transform. What happened? It is not fitting. Oh, pan. Same type of error is coming. Okay. Yeah. Okay. Okay. Fine. I will go through it. Okay. This is the mean square error. And now just we'll go through this printing part. This visualization needs to be done. Okay. Yeah. This X level is something. Let me just name it to X. And this is the Y value. Polynomial regression on California dataset. California housing dataset. Okay, this function is giving me label. Okay, let's see what happens. Yeah, as you can see, so it's coming in some sense as a parabolic function because the degree is 2. So you can consider this y equals to x square. Y equals to x square is a function like, what does this structure denote? Parabola. It is coming like a parabolic curve, right? Okay, now let me just increase the degree. So as you can see, something is coming over here. Degree equals to 5. This part is there is one outlier over here, it seems. Okay. And yeah, this is the pretty much the thing. But what happens is, what I wanted to show you is that what will be the thing if I just showcase this thing in this form of just the y train and the x test and y test is fine. X range and y. Okay. If I just see this thing, right? X train, y train. What will happen? X for PLT, X range, Y range predicted. X range. No, it's not that same thing. Okay. X train. Okay, this is the degree plot, right? X range. What is X range over here? X range all equals to poly dot transform X max. Okay, X range poly dot predict X range poly. Okay, fine. Yeah, essentially what I wanted to say is that as you increase the polynomial degree over here, may happen that, okay, let me increase it more. Okay.
Sir, one small note.
Yes.
So degree depends on the number of features. Suppose here we have 8 features. We are
Yes.
selecting degree as 10.
Okay.
So is there any relationship how to select the degree depending upon number of relationships, number of features?
A number of features as in
It is allowed to take degree more than the number of features. Here we have selected degree as 10.
degree as 10, yeah, degree as 5 also you can say. So what happens is that as you increase the number, the degree number, right, as you go into the higher and higher dimension, what happens is that this data gets overfitted into the model, and it may not produce the desired result what you wanted to expect in the test scenario. That's also one of the issue. So it's a crucial, like,
Here randomly can we see for 3 or 4 degrees,
yeah,
2,
yeah,
7, 10 like that? Can
yeah,
then
yeah.
we
That's
can
what we
observe
are.
how the curve changes.
Yes, yes, sure. So for the 2 degree, you have seen it. We were getting a parabolic curve, right? So now I have changed into a 3 degree. Okay. You can see, right? This curve is coming like this. So maybe this feature which I have selected, that's concentrated more on this side. So that's also maybe one of the reasons. So I had done this thing on the diabetes dataset. As you can see, this is what I was getting for a degree 10 for the diabetes dataset, right here. So these also depend upon the features. Maybe the feature which I have taken over here, it's not actually correlated with the y value. So that's why it is mostly concentrated over here. But in one sense, it can happen like this, and it may also happen if your data is super clean. Then what will happen is that this curve will pass through most of these points in the test scenario, and it will fail in the in the train scenario. It will pass through most of the points. It will fit perfectly, and in the test scenario, it will fail. Okay, so that's the issue of what we call as overfitting a model, right? Okay, okay, yeah. Yeah, so just a second. Now, maybe I can just show you this notebook as well. So this notebook I prepared beforehand. So maybe parallelly I can also show you this thing. Let's see what happened. It's not connecting. Okay. And in the other data set, we may we can try to implement whatever we said on this uh, skb.fit transform x comma y. That thing we can try on in the other notebook. You want to say something?
So yeah, as you explained here, we can select only one feature to draw the curve.
Yes. Otherwise, it's yeah. How will you fit uh, say suppose n-dimensional feature into a 2D plot?
Okay. So just like in a linear regression, is there may be some equation to give output
Hmm.
for multiple features.
Hmm.
So in simple linear regression, we have only one feature. In multi, if we have more than one feature also, then only we can apply linear regression. Like that
Hmm.
here also, is
Hmm.
there any that means we can combine 3 or 4 features to get output, and
Hmm.
can we draw the curve between the combination of those inputs and output?
Yeah, you can always this we are actually doing a curve fitting only, but the thing is that how you are going to plot that curve in a two-dimensional sense. That's the major question.
So that means in transformation also sometimes some features can be combined.
Oh,
Two or three, two or
what
three. Can
yeah.
we can we combine 2 or 3 features to get new feature and draw the curve?
Combine 2 on 3 features. So yeah, let me just clarify this thing. So the first thing is that this whatever curve we are drawing is a 2D curve, right? Where the x denotes some feature, right? And yeah, the y here denotes the predicted value. Predicted value. Now, what I was saying is that X is a some form of one of the X, you can say it's a some form of vector, you can say, right? Vector means some arranged collection of data which lies in some kind of dimension, some n-dimensional features, you can say. Now the question here is, and y is, of course, this is y is equals to just for one of this value, there will be some one single scalar value. This is, I'm talking about one of the features, one X with n features is equal has some y with a scalar value, right? Now the question is that how are you going to plot this thing? This is X n features, dimensional features, right? And this is scalar. How you are going to plot this part into a two-dimensional sense? It's not possible.
So in transformations, we have polynomial transformation. Can we apply this here?
So polynomial transformation, what it does is that
if it has multiple features, suppose if there are 2 features or 3 features,
yeah,
so if degree has 3 or 2, suppose take degree 2 and we have two features. So new feature can be created like x1, x2, x1, x2, x1 square, x2 square. That is like that. It was explained.
Yeah, that also
transformation.
Polynomial features also it's happening like this. The same thing is happening. This is also the same thing is happening. This is going into some higher dimension, some higher dimensional, as in some x comma 4 x comma 3, like this. This degree is there. But again, the same question lies that how you are going to plot this n features data into this two-dimensional plot. What you can say is that you can plot this thing, this sum w1 x1 cube plus sum w3 x3 cube plus sum w something like this is okay. Let me this name, and this is sum wn. This is essentially y predicted. Now this will be a scalar value. This you can see. This you can plot.
Yes, that's what we may not know exactly the function which is transforming into this, but output will be given by the transformation.
Yes.
Transformation. And then we can plot into two-dimensional plot.
Yeah.
So the input is the transformed feature, and output is the whatever it predicts.
Y predicts, yes. So this we can plot. This, if you want to see, we can show it over here, right? Okay, let me just for this sake, let me just plot it so that these things become clear, right? Y predicted and Y test. So remember this here. Oh, sorry, this should be x-axis, right? Y predicted.
Sir, my request is please take the 3 features.
3 features.
Any 3 out of 8 or 3 or 5, whatever it may be your choice. Then transform those three features using polynomial features transformation, and it will be the independent variable on which is to be
let's try
instead of single variable.
Okay, no issue. Let's try it over here only. So np.new axis. Okay. What we can do is that we were naming it some in a different sense, right? Okay. Okay, let me just check the what is this? This 2,1. This what this thing is doing. This is 0, np new axis. Okay. Okay, no issue. Go through this, right? Just a second. Sometimes remembering this code is also a heavy task. What was that name? We were importing the housing data set, right? Housing data set, housing fetch California. Yeah, here we were importing that. Okay. So let me do it in a better sense. What we can do is that first, let me print the features over here, right? What is X? So this is the mere, right? And what I can do over here is that I will, so how many features are there? 8 features are there, right? 1, 2, 3, 4, 5, 6, 7, 8. PLT dot subplot 4 to the 8. So maybe 4 rows and 2 columns. So, okay. So that we don't miss some essential features, I am doing this. Okay. Average bedrooms. Okay. Oh, wow, this is super fast. Okay. If we can make it a little bit big, then PLT dots figure fix size equals to maybe width is fine, but we want a better height also. So, yeah. So let me know which features you want from here. 3 features you said, right?
Any just how to select
Okay.
and how the graph will be shown like that. We have to observe.
Okay.
It's
Okay.
your choice.
Okay. Let me just take this first feature. And maybe these last 2 features.
Better to select which have positive correlation.
Yeah. So how you will say this thing, this one,
Yeah, yes, sir, that one.
this 2, and one more.
Okay, 1 and 2 we can select, and also fifth one also we can select.
1, 2, 3, 4, 5. Fifth one you are saying this one. Okay.
Yeah.
Okay. What is the name of the fifth one? So okay. Code. So here we will just pass the name over all those features. So here is medicine income. Okay. And the second one is house age. House age. House age is the second feature. Let me just copy paste it so that there is no scope of issue. And the third is fifth. You said fifth. So fifth is the population. Okay. What happened? Why is it throwing error?
Can we give a new name? Yeah, some X3 or like that.
So you need to put it in another bracket.
Square bracket.
What? Like this?
I think we have to put dot copy.
Yeah, in another square bracket. Yeah.
This like this we can do, right?
Yes.
No, just one whole.
No, sir. One
Entire
single
thing
square
in-
bracket of.
No, single square was there already.
Square within square.
Yeah, square.
Correct. Square within square.
Square within square, dot copy.
Okay, like this square you are saying? This
Yeah, one more.
Initially what you have written, right? No, that square bracket.
okay, the square brackets, okay. Fine.
Malli again one square bracket.
Again one square bracket.
No, after x.
After X. Yes, can you just paste it over in the chat window? That will be better. You don't need to give the names of the columns, just give me the syntax. Oh, okay. Wow, nice. Yeah, that's done. Okay. Degree?
So we have to put dot copy also after square brackets.
No,
We have to put.
I have send it to the x variable only now.
Okay, okay.
Yeah. So degree three,
Maybe three or three like that.
3. Okay.
Uh,
Yeah, this was the extrain, right? Okay, this is the extrain we are using here. It's not the expoly, it's the extrain. These are the column names we are using. Okay. Mean square is error is 0.61. Okay, now what you were saying. Is this the thing you wanted to see?
so this is the transformed feature.
Yes. Let me just name this polynomial x level. No, this is the actual versus predicted values. After this polynomial features, we are transforming it to the predicted value, right? Over from there, you are printing it. So maybe this labels will make it clear. So this is the actual value and this is the predicted value after combining that thing.
Okay, now can we plot the okay like the polynomial curve?
Polynomial curve you are saying this curve.
That type of curve. Then we can visualize which curve will fit, which type
uh,
of curve will
uh,
fit.
okay, okay, so let me just take this thing over here, because the other code won't run because this is a 3-dimensional feature. So I will just try to okay, X ranges. Just bear with me for some time so that I can just write this code properly. So here it will be y test is the x-axis. So this is y test mean, and this will be y test sorry, y test max. 100 dot reshape polynomial x range poly is x range. Y range predict is model dot range royal x y x range. Y range predict. Okay, so this is predicted. Let me. Sorry about that. Okay, maybe I can just plot this thing. It's not needed. It's range poly, right? So instead of this thing, we can just, instead of using this y test, we can just write it y test and something like don't know this will come as smooth or not, because in that time we were creating some artificial data to showcase the plot properly. Yeah, this will come like this only. Because here what we were doing is that we were creating some artificial points, some 100 artificial points, and then we were trying to fit this data. But yeah, similarly we will get something, some sense, in some sense a curve we will get. Not sure like how to generate this thing now. Maybe I can try it afterwards to create some artificial data to showcase the curve properly.
Okay, now for this, what is the accuracy, sir? What we have done till now? What
So
is the accuracy?
the mean squared error is coming as 0.61. Mean squared error is coming as 0.61. You want to see any other degree? Degree 4 or degree 10 maybe? Maybe just maybe.
No, I think this is enough just to how to
Yeah.
manipulate the things. I asked. We will try according to the different combinations.
Yes. Maybe I just show you some higher dimensional feature. What will happen? Let me just try to do this. And yeah, yes, somehow it increased mean square error because it's actually fitting the line, that thing. So but the thing is that if I y predict right here, if I change it to just note this down, okay, let's see what will happen. Mean square error for the trained data is 1.31. This is for the unknown data which we have not seen for the training sense. But what will happen if I just predict this thing on the, sorry, okay, it's some kind of caching is there. Maybe I can just, so you can try it out. You can see some, in some senses, like this prediction error will be very less when you are going fitting a higher dimensional curve onto the training data. The training error will be very less, but as compared to that, the test error will increase, because in some sense what we are trying to do is that we are overfitting a model, overfitting the data, right?
So can you show the error on X test poly?
Now it is same, but yeah, you have to, now I don't know why it is same, because maybe the degree is very less, but maybe I can just go to higher degree and then we can just see what happens. Okay, it will take some time because mean square error, this is the test error 1.31, and this is this thing. But what will happen if I see this thing on the train data set? Okay, it's coming same. The train error and the test error both are coming same now. But yeah, you can just play it around and you can just see like what are the demerits of using a higher degree and what are the merits of using lower degree and all. So this trend of using a higher degree as compared to a lower degree, and what should be the tuning, how should you choose this polynomial degree, okay. And yeah, now, yeah, let me see if it's, this thing is working. Okay, yeah, this was the thing. This is the diabetes data set. Yeah, now the next thing which I was going to implement was this. So I will not write it down now. So I just have this thing. So I will just try to run this. So now we will implement the whole thing in a pipelining sense. So as you have seen this linear regression and all. So instead of linear regression, we can also use, in a similar fashion, we can use the SDD regression. And as you know, this is the XDD regression. This is these are the parameters which needs to be passed. So maximum iteration, and this, what is this toleration? I think this hyperparameter name, and maybe we can change the hyperparameter again and check this. So these are the different stages. Here I have also implemented the standard scalar. So these were the three different stages, steps which we are implementing sequentially previously. But now what we have done is that we have bunched them together in the pipeline, and this pipeline is executing each of these steps sequentially, and then it will return out the model. Yeah, so yeah, in some, okay, maybe I, since we are going to this thing only, let me use here only, no issue of writing it again. Okay, no problem. Okay, SGD regression, I think okay, I have to change certain things now. X train, Y train, model predict is, this will be X test, and this will also be X test. so that there is no issue with this, what they call caching issues. I'm just writing it down to the previous version. Okay, what happened? Okay, the training degree is too high. Okay. Or what we can do is that we can maybe we can just skip those cells. Yeah, we got this, and we took this 3 features. We are doing this trend test split. Now we can just omit this stage steps currently and directly move to this this pipeline part. Degree equals to degree. We have mentioned the degree as something. Maybe we can just reassign it over here as well. So here it is has degree, so that there is no scope of confusion. We will write the degree over here again. So degree equals to 3, and the FGD regression maximum iteration equals to some 1000 maybe, and we will fit the we will fit the X train and the Y train. Let's see. Why suddenly polynomial features, but what happened? Okay. No problem. Happen. What is the issue? X has 20 feature, but stand X 53 as input. Expecting 3 as input. Okay. Pipeline.xpredit. Why is it not working, this thing? Maybe you have to check this.
So just check once what is X train shape.
Yeah. What?
Just check once, like what is the shape of X train, and then
No, it's working now.
so but this is very high.
Very high, yeah. So here we were using this linear regression. Maybe we can just stick to it, linear regression for now. Then let's see. Fine.
Yeah.
ASDD regression, I don't know. Maybe sometimes it's because it has maybe it has reached some kind of local minima. It may get stuck over there. So there, this hyperparameter tuning plays an important role, and from there you can go to the global minima somewhere.
Mm.
The stuckness of this, we don't know how this curve looks like, right? And how is it moving and where it gets stuck. So that's one of the issue with the STD. Yeah, now what we are yes,
Can we use polynomial regression?
polynomial regression as in we are using the polynomial regression only, right?
Okay, there's no separate. Okay. So
We have done this.
okay.
So what I was saying is that we were doing this all these steps, right? All these kind of steps we are don't consider this kind things. We are saying that we are performing this poly trade poly all these things. Instead of performing all these steps, we are we are sticking them together into some module, and that's the point of pipeline, like, so that you can appreciate what is the usefulness of pipeline in this kind of scenarios. Okay. Yeah, so here you can see this is the polynomial part, and maybe we can just yeah, we can use this SGD. Let's see. uh, SGD linear equation sklearn. We can just see if we can maybe if we can just reduce the error somehow. Penalty alpha equals 2.001. Alpha is the training, what they call this thing, right? Uh, it's still high. It's not, maybe it's not fitting it properly.
So if you increase the iterations,
Yeah, I have increased into 10,000.
more, and
No, it's not helping. So what will happen is that it may shoot it up somewhere else also. So that's also an issue with this SGD regression. Okay, maybe we can just stick to the linear regression only for now. And yeah, yes, we can also check this out. What I was going to say about the linear, the other functions, right? Yes, okay. Let me just copy paste it. Okay, now let me just switch it back to linear regression. Okay. Yeah, so as you can see here, I have named all these things, models. The penalty I have termed, I have introduced this L1 regression, L1 regression, L2 regression, and the elastic net, which is a combination of, L1 and L2. And we will implement and see what's the error of each of this category. Okay. Let's see. Yeah. So L2, L1, and elastic both are giving me the same mean squared error, 0.60 over here. So yeah, what it does is that, as you guys, as I've said before, that you are introducing some kind of penalty term instead of just minimizing something like. Okay, let me just write it down over here. We are trying to minimize this thing, right? In some sense we are trying to minimize this thing, right? So
Sir,
yes.
in this pipeline, the one we have written above,
Mhm.
we are using both reached and lasso sequentially.
Region lasso, yes. We have used all the four models. We have implemented this linear regression without any kind of penalty term. Then we have introduced ridge regression. Then we have gone to lasso, and then at the end we have implemented elastic net. You can also in the SGD part you can just change this thing to the SGD, and in the SGD part also you can write the penalty term over there as well. Is it clear?
Sir, I did not get how we are using that. Is it
Okay.
in a loop or for
Okay.
naming?
Okay. I will get to it. What is this data structure called anyway? So anyway, some speak it's, I think, dictionary. It's called dictionary. So, so this I have arranged it like this. So there is this linear regression, and correspondingly, this is the model name. This is the L2 regression, and this is the correspondingly, this is the model name, model with the hyperparameter, and this is L1, and this is the corresponding model name. And this an elastic net regression, and this is the corresponding model net, right? This is the complete data structure. Now here what I have done is that name comma model in models.items. So these are the items, right? And the
Okay,
name,
okay, in the tuple form, right?
yeah, tuple form. The names will be names this, and the model will be this. And I'm passing this model name, model this thing, this model I'm passing over here, linear regression. Okay. And for the naming part, I have, I think here what print name. So here I have mentioned the name, the model name. Yeah. So in a tuple form, it's going through each iteration and giving me this this error terms.
Okay, okay.
Yeah. And what I was going to say is that we are going to discuss this thing. So what happens is we are trying to minimize this thing, right? And in purely sense that these are the measurements, this is the predicted value, and sorry, this is the actual value and this is the predicted value. Some people write it as wx comma, maybe I just write it like this. But essentially what happens is that this is the best case, but there will be some issue because noise will be added, right? And also there is something called as this w, some of the weights may shoot up as well. So in those cases we may use this what is called this regularization. So what it means that we are adding some kind of penalty that okay, this there is some issue with, because of the error you may shoot to somewhere else, you may reach somewhere else, but because I am adding the penalty, it's like drawing the point more closer to the actual value. And yeah, so in the L2 part, you know this. So this is a huge topic, as you can, if someone is interested, they may go through this. This is one of the crucial thing for inverse solving the inverse problem. So anyone knows what is inverse problems? Okay, so you have something like ax equals to b, right? Or wx equals to y. Wx equals to y, this is called as the forward problem. And when you are retrieving back the x, that thing is called as the inverse problem. So forward problem solving is comparatively easy because you have some w, you have some x, you will get definitely a y. But when you are moving into the inverse direction, there will be an issue with the x, because there cannot be a single x which might give you the desired y. There can be a multiple x values lying in some dimension. So in those senses, there is a complete family of problems of inverse problems, mostly used in the imaging part. And yeah, over there you can also, it's used for compression and all. So here you have used, you can use something like this hyperparameter, so lambda or something, and yeah, some matrix is there normally like this. So there is a different notation, and this also plays a crucial role. So normally it is, if it's squared, this is called as, so if I make some mistake over this, I don't remember the exact formula, so it's better to go through the textbooks once. So normally this is called as Tikhonov regularization. I plays a crucial role over here. And when I say I means, I is what kind of matrix? Anyone?
Identity, sir. Identity.
What, sir?
I is
Identity.
what? I is a matrix.
Identity.
Yeah, identity matrix. So I is an identity matrix. This is the best case. Most problems use identity matrix, but it may happen that they have people have gone through this literature and they have found that I is always not the best choice. There can be other. There is a choice of I as well. So sometimes they use this Laplacian Laplacian operator. sometimes it's called differential operator. So it's a big problem, this and there are many ongoing works in this literature, in this area. So if anyone is interested, they might go through this. I don't know if anyone has seen this guy's video. Anyone has seen this? Okay. So if you want to see what this regulation plays a crucial role in this compressive sensing, this imaging part, you can also go to the Steve Brunton videos. So that's also a very nice playlist of how to this choice of regulation and all. And this problem is
Where,
there in
where
different
is it,
fields
sir?
as well. Yes,
Where is it, the video which you are referring to?
it's in YouTube.
Can you mention the name once again?
What? Can you be a little clear?
Can you mention the name once again?
Steve Brunton. Yeah, you may search it now only. So there is a guy with the specs and black t-shirt. Okay. Okay. So yeah, now this is the thing.
Sir, can you type in? Sir, can you type it in the chat, the channel name?
Let me see if I can. Let me just stop sharing my screen for now. If I can just show you this. Just give me a couple of minutes. Yeah, see, these are the things which I was saying. Robust regression with the L1 norm, sparsity, and the L1 norm. These videos I was saying. Okay, this is the channel. So yeah, let me just click over this guy's videos. Yeah, probability statistics, but I think you will get those things into the. So this person is essentially a mechanical engineer, but as I said, that these problems has their footprint on different sectors as well. So in heat theory and all, also these things plays a crucial role. So that's why he has done some videos over here. So yeah, you have to search it over here. But introduction to yeah, but I just searched that Steve Brunton regularization. I got this. Yeah, if you want, you may go through these videos. And yeah, as I was continuing that this thing, right, this alpha choice of alpha plays a crucial role. Alpha and L1 ratio, so these things plays a crucial role in determining the accuracy, right? And that's the part of what we call this hyperparameter tuning. And we will go through those things in the next lecture, next live session, on that is on Thursday, right? Okay, yeah, that's it for today.
Sir, one small doubt.
Yes.
Actually, I tried previous graded assignment with some other versions. So it was given that some 1.2.2 version I have to be used. How to use that version?
1 point?
Something exactly I don't know the code given. In the graded assignments, each you have to use so and so version they have given.
Okay, which library?
So that is of SQL.
SQL.
Okay, and what's the issue?
So how to use the particular version?
Yeah. So yes, okay. I can show you that. So essentially, what you can do is that Google Colab, as you know, is actually a terminal. So here, what you can do is that pip uninstall you can do, right? And pip uninstall is, yeah, it's coming over here, right? So here you will uninstall the scikit-learn, sklearn, whatever you have inside this machine. And then what you will do is that you will install it again like this, pip install. I don't remember the exact name, so sklearn maybe. So yeah, double equals to some 1.1 whatever version you are saying, 1.3, like this. So what you have to do is that you have to uninstall the previous version, and after that you have to install the new version with the specified name, like this.
Sir, I think we can assign it directly and it will downgrade to that, I think.
How? Where you are saying?
In there only, sir, I tried like sklearn dot underscore version underscore is equal to that the version required.
I have normally done like this, but yeah, if you are saying sklearn, then
Dot underscore
underscore
vers-
underscore
version
version.
is the same thing, is equal to that the version required.
What is the name of the version?
I think 1.2.1.
Equals to, is it?
Yes, sir. That's, I think it should be in quotes. 1.2.
Like this?
So
Yes,
it's
sir. I think
1.2.2, not 1.2.2.
1 point?
2.2.
No, this thing is throwing some error.
So it is the given in the graded assignment 4 itself. It is mandatory to use sklearn dot underscore version underscore is equal to 1.2.2. sklearn dot, I think it is double underscore
And sir,
version underscore is equal to 1.2.2.
Okay.
that's the just
that
the
im- that import should not be there, I think.
Then I am not sure of this command actually. I have normally use this uninstall and then install part. But yeah, I don't know how to do this thing. Maybe I can take a look and then tell you. But is there any command already given in the documents or anything?
No, just they give like this. You have to use this version to solve the. I think after version underscore equal should be there.
No, it was showing some error. Let me just check this. Sklearn. Achha, what will happen if I do this? What is the command to check the version? Sklearn version, right?
Print
No,
scaling version.
print
Scalar
sklearn.
underscore version underscore.
Just a second. Sklearn dot, right?
Correct. Yeah. Shift enter.
Okay, I have not inputted sklearn. 1.6.1.
Yeah.
Yes, sir. It is only one single equal to, not equal to equal to.
Okay. No, it's still
So
throwing some error.
Import should not be there.
there should be quotes 1.2.2.
No. Then how you are importing the sklearn version? Importing the sklearn then if it's
Sir, I have done like import sklearn in the first line. That's it. After that, sklearn dot underscore underscore version underscore underscore is equal to 1.2.2 in quotes.
Wait.
Like this. Yeah. Yes. It's working like this. Okay. Yeah. So, okay.
So, yes, this is the way how to install that version.
Yeah. But I don't know what could be the issue if you means maybe some data set or maybe something with related to some libraries and all maybe missing in the.
Exactly exceptionally for this week 4, it is given like that. You have to use so and so version. I think for remaining weeks also that will be given.
Okay. I'm not sure what are the issues with it. But let me just rerun this. Then we can see. If we find some error, then we can say that there are.
No, in the answers there may be some decimal points difference.
Okay.
So from version to version, accuracy may increase from
Mm,
version to version, but they will fit answers for this version.
mm.
So to evaluate the scores, I
Oh,
think it was suggested like that.
okay. Okay. Got it. Yeah. Okay. I think that's it. Okay. Any more doubts?
Sir, for remaining weeks, recorded sessions are available. So previous weeks, not remaining.
Week
Previous
one,
weeks, week 1, week 2, week 3, week 4.
week one, week two. Yeah. Everything is available.
Hello.
Yes. Yes. All the weeks are available in the YouTube channel.
Okay. Okay.
Hmm? Okay. Hmm. Any other question?
Thank you, sir.
Thank you.
One more small query regarding this OPP.
Yeah.
We have to turn off this auto completion, this thing, Gemini, this thing. I mean, in Colab.
I don't know. That's a valid question. I have to ask this.
Okay.
I'm not sure about this. Yeah, but I don't know whether you can turn it off or not. Also,
That's why. That's why I was asking.
it's completely new. This thing was not there previously. So yeah.
Okay. Okay.
So OPP up to 4 weeks or fifth week also.
Fifth week, let me check.
OPP 1.
OPV one. Let me check the mail. Then I can tell you. Just give me a minute. OPP.
Because there is some mixed concept between 4 and 5.
MLT, OPP slot, OPP one. Just. Anyone has that mailed open? MLP. Week 5 data assignment. Okay. OPP 1 is week 5 till week 5. Is it clear?
Yes.
Week 5. Okay. Okay.
That too up to polynomial regression.
OPP is on 27th, right? So high polynomial week 5 is covered till hyperparameter tuning. So that's the last part remaining, which we'll cover on Thursday. Basically, we will go through the random search and the grid search.
So OPP is on 1st March or
1st March maybe. Oh, sorry, this is the division session. Okay. Let's taking the division session. Okay. Yeah. Anything else?
Okay, good night,
Any
sir.
other question? Good night. Good night. Thank you.
Thank you, sir. Good night, sir.
Good
Thank
night.
you.
Thank you.
Good night, sir.
Good night. Thank you. Ravikant, Sahil, Anthony, Sadia. Ravikant, Sahil, Anthony. Are you there? Okay. Sahil, Anthony, you have any question? Okay. Thanks for joining. Yeah, do you have any question? Sahil, Anthony? Sahil, Anthony, you have any question?